Hi. In the last video, we took a look at the SPI serial EEPROM and started building out the tools I would need in order to start making use of that. Today we're back on the emulator and I want to take a look at the ALU flags. Now, I quickly mentioned in the past that there were some issues that I needed to identify and get to the bottom of related to the ALU flags and how I was going to handle those. There's nothing technically wrong, I just have some design decisions to make related to that. I want to get into that today and try to articulate what the problems are and make some decisions on which direction I'm going to go. Let's get into that. Hi, I'm Adam. I'm still building a 16-bit computer from scratch. I'm no expert here. I make lots of mistakes. So many mistakes I've actually had to reboot my computer build. I hope you will find my journey interesting, and I hope you will join me as I learn along the way. I've been trying to think through a dilemma for a few weeks now. It's related to the ALU and its flags. It starts in the idea that my ALU is going to have three distinct operational units. It's going to have the ALU adder, which we've seen. Subtraction is still pending. It's going to have a logic unit, which I haven't gotten to yet. And it's going to have a shift unit, which I haven't gotten to yet. With three separate portions of the ALU wanting to feed the results onto the main bus, and me having to calculate flags based on the results of any given operational unit, I originally started out by creating an ALU internal results bus. That even remains on the high-level design graphic that I use between video segments today. There's another solution I want to consider. Now, I could allow each of the three operational units to assert their results out onto the main bus directly. And more I'm leaning towards this solution. It would simplify things. It would reduce the number of gates I have between the results and the final latch. But which one's better? The short answer here is yes. And the longer answer is it depends and varies. So a lot of that depending and varying is going to be contingent on how we look at the problem. Starting with getting the results to the main bus, the solution seems simple. Let each operational unit assert out onto the main bus directly and eliminate all the extra complexity of the internal bus. Again, fewer line drivers, fewer gates, and less time to get the results out onto the main bus and ultimately latch it. But once we start talking about how to calculate the flags, things complicate a bit. In my build, there are 5 flags that need to be calculated. The Z or 0 flag, C or carry, N or negative, V or overflow, and I have introduced an L flag to simplify the calculation of conditional execution. The L flag is going to be derived from the N and the V flags, and I'm going to ignore it in our conversation today. If we keep in mind the fact that flags may be calculated many times before they're actually latched, and only latched when they're relevant, we can consider more obscure methods for calculating these flags. The ALU internal bus makes the source of the calculation nearly trivial for each of the flags, but can we do better? The Z flag is set to true when all of the result bits of an operation are 0. These results come from the ALU adder or the ALU logic unit, and I really see no reason to evaluate the Z flag on a shift operation. If I'm off base here, let me know. Now I can take the results from the ALU adder and the ALU logic and evaluate them independently and then select the proper unit's Z flag result to latch. Or I can also look at the main bus and calculate the Z flag directly from the contents on that bus. Again, the Z flag would only need to be latched when it's relevant to do so. The C flag is the carry flag, also sourced from the ALU adder and ALU shift unit. It can also be manipulated directly by software. It really is an extra bit on calculations and therefore does not fit on the main bus. It is best suited to come from the ALU directly when not being manipulated by software. The N flag is really the contents of the most significant bit on the ALU adder. It does not make much sense to source it from the ALU logic or ALU shift unit. That said, it could just as easily be sourced from the main bus and ignored when not relevant. The V flag is kind of like the C flag in that it can be manipulated directly by software. However, it's also similar to the N flag in that the only real source for that flag is the ALU adder. The ALU logic and ALU shift units do not really come into play. And there's really no good method for calculating that directly from the main bus. Other inputs are required. All right, so Adam, what are you going to do with these flags? How are you going to calculate them? Well, it's not going to be consistent. The Z flag makes the most sense to come from the main bus, and only lasts when it's relevant to do so. It may open up some other possibilities for capturing a Z flag during other operations. We'll see if that comes to play or not. I'm not exactly sure, but that's the path I'm going to go. The C flag, being just a 17th bit in some calculations, will be multiplexed with a 74 HC151 IC. Simple enough to handle. It's overkill for the 8 bits that it can multiplex, distilling that down to just 2. The N and the V flags are only relevant from the ALU adder, and they can even share the same control signal. When one is latched, they both will be latched. Since the N and the V flags are both sources into calculating the L flag can be controlled with that same latch signal as well. But we're ignoring the L flag. Anyway, both the N and the V can be sourced from the ALU adder, and that's easy enough to take care of. So let's make that the plan. I'm going to go ahead and start updating the emulator, and I think I've got some components I've got to build out for the emulator, and then I've got some work to do to tie that all together so that I can display and calculate the results flags. I'll be back in a bit. Okay, I thought I'd start with something very trivial, and that is getting the X flag populated for both the program and the interrupt flags registers. Now, the X flag is going to be used to indicate context. It's not going to be visible to software, but I am definitely going to need to be able to use that in determining how to execute code. And so that's actually going to be feeding into the control logic for the control word lookup. All right, so the program flags has the X flag set to off or 0. In the interrupt flags has the X flag set to 1 or high. Okay, so what changes did I make? Well, I have the ALU flags module, which is starting to be built out here. It's incomplete as it stands right now. And of course, I've got the C code that's associated with that, making sure that it gets on the screen properly. I also updated the computer, and I've got 2 new components that I'm putting on the computer. One is the program flags, one is the interrupt flags. Yes, that does imply that I will be building out 2 of these ALU flags modules and being able to swap back and forth between them. Okay, now let me look at the Z flag. Next along here is the Z flag or 0 flag. Now that flag in the ALU flags module takes the main bus as input, and if all of the bits are off, it sets that Z flag high when this latch signal is on. So if I turn it on the next clock cycle, it will latch the Z flag. If I turn that back off, it will keep that Z flag. And if that main bus continues to change, the Z flag stays latched until I decide I'm going to latch it again. And now that the main bus is empty or is not empty, it turns that off. Again, I'm not latching. It's now got zeros. When I latch, it will latch the Z flag. So that's working as expected. And like I said, I haven't wired up the interrupt flags yet. I'm going to save that for another time. The key here is I'm only sending the signal to the program flags to latch. I am not sending any signals to the interrupt flags to latch. That would be handled in the control module, but because they are exactly the same code, just different controls, I'm expecting that the interrupt flags will work just the same as the program flags. Next step is going to be the carry flag, and that again is just an extension of the adder. It comes right off the ALU, so I will pipe that into the program flags and get that working. See you in a minute. Okay, the carry flag. Now, just like the Z flag, I've got it set up so that it doesn't actually latch the carry flag until I've got the signal asserted. So I can easily assert out onto ALU A and ALU-B such that the addition out on the main bus now contains a carry, and then it will latch that when I set the carry flag latch signal high. Again, I'm working with the program flags. The interrupt flags should all work the same. Okay, so the one thing I do want to spend a moment here on is how the carry flag itself gets selected. Now I've got two different sources identified for this, and really three that I could possibly use, but I am anticipating that the logic unit is not going to have any value adding a carry flag into it anywhere. So I am going to have it set and ready to go because I have the room for it, but I'm not actually going to ever use it, at least not yet. I may have something else that I might want to wire in there, and we'll make that determination when we get there. Anyway, what I'm using is a 74HC151 multiplexer, which has 8 inputs, and depending on which of those inputs you select, it multiplexes that into a single output. All right, so I have 3 different signals I can use to select one of those 8 inputs. And I chose to use the assert signal for the ALU adder and the ALU shift unit. Those 2 operational units of the ALU will be used and actually output a carry flag potentially. Selector A, which is the least significant bit on the 3 bits that select which output, I'm going to use the adder assert to select the carry flag coming off the adder. B is the middle bit, and that's going to come off the shifter. And then C is the logic unit, which doesn't make a whole lot of logical sense, pun intended. But it does offer me an opportunity to be able to select something else, which may be useful for piping a carry flag into what gets latched. And so that means that I have to wire up my data appropriately so that when A is selected, B and C will both be low. Only one thing can assert out onto the main bus at any given time. So that's pretty much guaranteed. So data bit 1 ends up being the carry flag coming off the adder. When the shift unit is asserting out onto the main bus, I am interested in its carry flag, and that will be presented on data bit 2 of the multiplexer. Data bit 4 would be what might come off the logic, or if I end up replacing that with something else, then that would be associated with data bit 4. Right now I've just got it pulled low. So if it just so happens that none of those 3 are asserting out onto the main bus, then it's going to default to data bit 0, which I've got pulled low by default. I'm not going to use that for set carry or clear carry. I will have other mechanisms for that. Okay, and here I've added controls for set carry and clear carry, and they're almost trivially simple. I click set carry and the carry flag comes on. I click clear carry and the carry flag goes off. These happen asynchronously of the clock, so there's no integration into that at all. All right, next up on the list is the in flag. Let me get that working. The in flag deserves a little bit of conversation about how it gets implemented. Now, I said I was going to take that directly off the ALU adder because it really has no relevance to any other functional component on the system. But it doesn't make any sense to add an extra signal into this particular flags module just for the sake of taking the data directly off the adder itself. When the adder is actually doing something meaningful, it will be asserting out onto the main bus anyway, and I have pulled the entire main bus in for calculating the Z flag. So I might as well go ahead and make use of that particular signal that already exists. And that's what I did. So if I set up an addition where my result is a negative, and I say go ahead and latch that, the in flag gets latched. And then, of course, if I set up something where the most significant bit is off, the in flag gets latched as a 0 or off. Now, of course, I can turn off the latch signal and make changes, and the contents of the flag maintains just as it should. Next along in the list is the overflow flag. Now, I've got what I thought was a pretty elegant solution for being able to determine the overflow flag and pass that along into the flags registers respectively. But in video 60, where I talked about the ALU design, a comment was left by GC Ewing, which caused me to take a step back and rethink this. And basically his comment straightened me out. In typical Adam fashion, I brute forced and over-engineered the solution to the problem, when there was something far more elegant that was out there, and that was just to take the most significant bits of the ALU inputs and compare that to the resulting sum, such that if the most significant bit of both the input and the sum changed in any way, then you've had an overflow. His comment is pinned on that video, and it is an important comment because it allows me to then turn around and simplify that V flag calculation quite a bit. It also, I believe, is going to be faster because the reality of the situation is if the carry bit from the fourth IC of the adder into the fifth IC of the adder is set, then it actually delays the calculation and ultimately makes that whole process slower. So I believe that even though this is one gate deeper in the ALU, it's actually going to be a faster response time. It shortens that propagation delay for sure, which was one of my problems. So that said, this is what I have managed to come up with. And so I have set and clear overflow, just like I do with the carries. And if I now latch the N, V, and L flags, if I set up an overflow condition, you'll notice that the V flag gets set. If I remove that overflow condition, the V flag gets removed. So this is now working as expected. The final flag here is the L flag. Now that will be high when I have a negative but not an overflow, or an overflow but not a negative. And that's going to be latched again with everything else. So I have a negative but no overflow, and I have a less than flag. Here I have an overflow but not a negative, and I have a less than flag. When I have neither or both, the less than flag is clear. The final thing I want to do in this video is I want to circle back to the ALU adder and simplify things a little bit. Now, I anticipate this is going to be a bit of a challenge, and more than likely the best way to go about doing this is to break everything. And how I'm going to go about doing this is I'm going to rename all of these ICs and remove the last one, so that other than bits 0, and let's just go ahead and make that 0, 0 just for the sake of argument here. Yeah, we'll just leave it at 0, 0. I can come back with a quick rename after that. So by doing this and then compiling everything, I'm going to put the compiler actually to work for me to find all of the places that I need to review and make sure that I get things buttoned up here. It makes it a little bit easier than missing a complete section of code accidentally somewhere along the lines and have things crossing and making it a little bit more difficult to debug. Once I've got all the bugs worked out, I can come back with a quick rename of bits 0, 0 to bits 0, and that'll be a quick fix after that. Let me get going on this from my side. It'll take me a little bit to complete. I don't expect this to be a quick 5-minute job, but you never know. And then I'll come back with the last presentation of the adder working with the flags. Be right back. Okay, here's the adder cleaned up. Let's go ahead and latch all the different flags and start asserting values out onto the bus. And you can see that it is still tickling the correct result bits. That definitely looks right. I'm happy with this. Well, I'm certainly happy to be at this point. I now have the ALU to the same point that I have it in the actual hardware build. And I'm emulating that properly, and I'm pleased with where I've gotten to. I've even been able to realize some optimizations for my work. Next up, I'm going to be back on the EEPROM replacement. I do still have some work to do to be able to move a binary from my host computer after I build the control ROM and send that down to the actual EEPROM. I still also need to be able to work on how I'm going to get that from EEPROM to static RAM during reset. And so I've got some work to do there to ferret those bits out but I have hopes that I'm going to be able to get that done relatively quickly. So I'm back on that in the next video. Coming up soon, I am going to have to revisit the ALU and the build and pull that back out and see if I can't bodge and splice and hack and improve my build to the point where I can parallel what I'm doing in the emulator. Yeah, I still need new PCBs, but I'd like to see at least some of this working in hardware before I actually go about building and ordering new PCBs. So that's the roadmap for the next several videos. We'll see you soon.